preprocessing for both SAT, MaxSAT, and QBF. And we have three excellent speakers on this topic: Benjamin, Jeremias, and Martina. We will talk about each of these topics respectively. And so for example, there's been several talks during the workshop on encodings and other areas, but one of the most important techniques that has been developed in different areas, and especially in SAT and QBF, but also in MaxSAT, it seems to be one of the most important reasons for progress is actually preprocessing. And preprocessing has helped to really kind of re-encode formulas, make it much easier for them to solve. And I'm excited to hear about these techniques for these three core parts of SAT and related areas. The first speaker is Benjamin Kiesl. He's also co-author of the new preprocessing chapter in the Handbook of Satisfiability, the second edition. And yeah, I'm excited to hear what he's going to say. Could you please share your slides and take it away?
So can you see my slides? Hello.
Yes, I can see it.
And you can also see them in the slideshow?
Yep.
Great. So thank you, Marijn. So I will be talking about preprocessing and SAT solving. And as Marijn mentioned, I was co-authoring a handbook article on that. During my PhD, I was also working on that topic, not only preprocessing and SAT solving, but also in theorem proving and first order logic. So yeah, let's see. I tried to keep this high level to give you a few big ideas. And I hope this will get you interested into diving deeper, not during this talk, but then after you've heard this talk. So here's the overview of what I'm going to tell you. So I'll spend some time on the motivation behind preprocessing, why you do it, what you should consider when you're doing preprocessing. And then I will just give a few examples of popular preprocessing techniques. And there are in fact so many that it would never be possible to cover all of them. So I thought I'd just choose a few popular ones that give you the ideas of what's going on when you're doing preprocessing, or that give you an idea of how such preprocessing techniques what they could look like. And then I'll end with a few concluding remarks to see what we saw. So the motivation. So I normally, when I would give a talk on SAT solving or something, I would start with that slide here, but I thought that one was nice also for preprocessing. And I put the S in application here into parentheses. And the reason is because the application of SAT solving is very important to preprocessing because of the following. So what you normally do, and I guess most of you know this, but just to recap, you have some problem from some problem domain, like formal verification, bioinformatics, security, what have you, some problem domain. And when you want to solve a problem from such a domain using SAT solving, then what you do is just you take the problem, you transform it into propositional logic. So you then get a formula and propositional logic, and then you throw a SAT solver at it. And once the SAT solver is hopefully successful in solving the problem, you get an output. And then in many cases, you decode that output to get a solution to your original problem. But this encoding phase into propositional logic is also one of the motivations behind preprocessing, because this is often done by a script you would write. Like when you're doing software verification, you might transform your code into propositional logic or something. And during that transformation, many things can happen. And you could introduce lots of redundant or unnecessary things into your propositional formulas that will not particularly help your solver. And that's why you then use preprocessing, because then you simplify what you get by encoding something into propositional logic to help your SAT solver a bit, so that it's easier that it has an easier time solving your formula. And so here's what's happening on a very high level. You get some formula in conjunctive normal form normally, that's the standard in SAT solving. And you could view such a formula actually as a set of clauses. And that's what I'll also be doing over the course of this talk. And in fact, you can also view the clauses as sets of literals. And your solver then tries to make this formula true by making all the clauses true. That's what would usually happen. Now with preprocessing, you add another stage that comes before the actual solving. And in that stage, you do simplification. And actually nowadays, what you also sometimes do is you periodically during the solving use typical preprocessing techniques to simplify your formula during the solving. And that's what you call improcessing. And you call it improcessing because the techniques are actually traditionally preprocessing techniques and not classical search techniques or solving techniques that you would have in a typical SAT solver. So as an example, you would, for instance, have this formula. The preprocessor considers the formula, looks at it, and what it can see is that the clause on the very right of this formula, it's a tautology. This means it contains Z or not Z. So this clause will always be true, no matter what assignment the solver searches. It will always be true. So this formula is not really helpful. This clause is not really helpful for the solver. So the preprocessor just throws it away. And then when it's done, it outputs the simpler formula. And then the solving can start. And now this is easy for the solver. It randomly chooses, for instance, to make X true. Then it's forced to make Y false. And then you get a satisfiable assignment. And that's basically it. That's what's happening. Now, the thing is, and that's really crucial for for preprocessing and SAT solving, that the modifications that you apply during this preprocessing phase, they must preserve the satisfiability status of your formula. And what that means is simply that whatever your solver would output before the preprocessing, the result shouldn't change afterwards when it comes to the decision of whether the formula is satisfiable or unsatisfiable. So you really don't want to change the results because otherwise something would be going wrong with your preprocessing. Now the thing is, I said you want to simplify a formula. And the first question you might ask then is, what does it mean to simplify a formula? What makes a formula really simpler? And the answer is that generally there is no real answer. You could think about removing something from your formula, right? And the intuitive argument would be that, yeah, you remove something that intuitively makes your formula smaller, so that could be simpler. And in fact, many preprocessing techniques do remove something, namely most often clauses. So that looks promising. However, if you remove the wrong things, that can have disastrous consequences. And I'll not go into the details here, but you can show that for certain formulas, when you remove the wrong things, you will exponentially slow down your solver. So that's really disastrous. So removing is not always good, but it can be good. Now, maybe you might want to add something if removing is not always good. So typical SAT solvers learn clauses during solving, so they add something. So you would think addition is good, right? But the thing is, especially during preprocessing, it's very hard to know what to add, when to add, and how to add. And if you add the wrong things again, this can have bad consequences. And finally, you could also think about modifying something, whatever that means, like taking parts of your formula, rewriting them. Could work or could not. But the conclusion is that whatever you do, it really depends whether that will work or not. And when you ask super experienced people like Armin Biere or Bahrain or whoever, so what really works? What should I do? Then the answer I most often also got that, yeah, it depends. It depends especially on the formula at hand and on what exactly you do when you preprocess the formula, what techniques you use, how you use them. So unfortunately, there's no free lunch. There's not really a clear answer. But still, we use preprocessing, and this cactus plot is what it's called, shows that it can make sense to use preprocessing. So on the y-axis, you see the runtime of the solver Lingeling by Armin Biere at the SAT competition instances of 2013. And on the x-axis, you see the number of solved benchmarks. So what that means is the further right a curve is, the more efficient you could say the solver was. And what we see here in particular is on the very left, the red solver was Lingeling with all pre and in-processing disabled. And on the very right, we have a version with most of the important pre-processing and in-processing techniques enabled. And the main takeaway from this is just that there is a significant improvement that is just caused by pre-processing and in-processing. So even though it's not clear what you should do in general, you can get a nice speed up by doing pre-processing and in-processing in practice. So now that we know that it can be good to do pre-processing and that it can help, I'll just cover a few simple techniques that can be effective and that should give you an idea of what you could do during pre-processing. And I'll start with the resolution rule. So most of you will probably know the resolution rule, but just in case, I wanted to add this here to make sure. So the resolution rule is a very simple deduction rule in propositional logic. And it says that if you have two clauses where one of the clauses contains a literal X and the other clause contains the negation of that literal, namely not X, then you can just merge the two clauses and throw X and not X away. And what you then get is, in this case, C or D, a new clause that you could derive. And you can actually show straightforward that deriving that clause, the new clause is implied by what you had before, by the previous clauses. This is all straightforward. And what we sometimes write here is this. We write this circle with a cross and an X to denote the resolvent of the two clauses upon X here. And I will use that in the slides later on. So let's start with a simple idea, namely to remove clauses for which you know that they're obviously redundant. That's something you could do for pre-processing. You just remove something where it's very clear that it doesn't help your solver. And one example that we have here and that you've already seen on a previous slide are tautologies, namely clauses that contain two complementary literals, X and not X. And here we have this example, A or B or not B. So that's a tautology because it has B or not B. And as I said before, such clauses are always true by every assignment. So they really don't help your solver if you keep them in there. They just make your formula larger. So you better get rid of them before you start the solving. That's just a very simple idea. Now, there's another kind of clauses, namely so-called subsumed clauses. That's also a simple but very effective concept. You remove clauses if they're subsumed. And what that means is a clause C subsumes a clause D if C is a subset of D, meaning all the literals that are in C are also contained in D. And here's an example. So A or B subsumes the clause A or B or not C. And clearly, every assignment that satisfies C, meaning that it makes literal in C true, must also satisfy D, because it also contains the same literals at least. And therefore, you can throw away the subsumed clauses. Those are very simple techniques, but as I said, they can be very effective. Now, when you implement subsumption and the removal of subsumed clauses, then there are actually, you distinguish two kinds of removing subsumed clauses. And the one is forward subsumption, which is straightforward. So you just go over each clause in your formula, and then you check if one of the other clauses in the remaining formula subsumes it. Now, if that's the case, then you just remove the clause, and you do this until you've removed all your subsumed clauses. Now, the name already suggests it. If you have forward subsumption, of course, you'll also have backward subsumption. And there you do it the other way around. You don't start by checking if the clause is subsumed, but you check if the clause subsumes something. So again, you go over your clauses, and then you check in the remaining formula all clauses that are subsumed by your particular clause, and you just remove them. And that actually works very well in practice. You can, the way you implement this, there are lots of details that you can read in our article, but that's the main idea what you can do with subsumption. Now, there's a very nice special case of subsumption and resolution, namely self-subsuming resolution. And when we look again at the resolution rule from before, then we could look at the special case where C here on the left is actually a subclause of D on the right. Then you take below C or D usually, but since C is a subset of D, what you end up is just D. And that's when you add D, here's an example. You have A or B or X, and then on the right you have A or B or C or not X. And since A or B is a subset of A or B or C, what you end up when you resolve these two clauses, what you end up with is just A or B or C. And then when you, in this case, add A or B or C, namely D here, then that's the same as if you had just removed not X from the right clause. And that's what you in essence do, because since the above clause is then subsumed by the clause you derived, you could throw away the above clause. And that's basically what self-subsuming resolution then does. So you have two clauses, C or X and not X or D, such that C subsumes D, and then self-subsuming resolution just removes not X from not X or D. So you remove literals from clauses, and that makes the clauses stronger, give you more deductive power.
Benjamin, Moshe has a question.
Sure.
So for many years, the conventional wisdom was that subsumption is too expensive; it's not worth it.
Mm-hmm.
What is the current wisdom about subsumption?
That's good because when we wrote our preprocessing article, then Armin Biere was really the main man when it comes to subsumption. So I think self-subsuming resolution, when you do the special case, this works well. But I think really that Armin would be the one who should answer this question, because he could do it way better than I could, if he's still here.
Is Armin, are you there?
Yeah, sure. Already back then when we wrote this paper, actually, João Marques Silva came to me and said, this is impossible. You can't do a subsumption all the time. But even back like 15 years back, it was clear there are a couple of implementation tricks that you can do it. And so you can play with both forward and backward subsumption. You need to add some limits. So like typical limits are that you're not doing this if a variable occurs more than 100 times. But if you do that, you can do this always until completion for 10 million, 100 million variables, no problem.
Yeah.
Yeah, please continue.
Yeah, so that's subsumption and self-subsuming resolution. Now we'll come to something where subsumption can help you speed it up. And that's called variable elimination. And actually variable elimination can be considered the most effective preprocessing technique in all of SAT solving. So if preprocessing techniques were basketballers, then variable elimination would be Michael Jordan, you could say. And here's what it does. So the simple idea is just you look at your formula, you pick a variable, and then you just add all possible non-tautological resolvents upon this variable. And once you've done this, you remove the original clauses that contain the variable. And what you end up with is a formula that doesn't contain the variable anymore. And that's the basic idea. And more formally, to define what it does, you can define a resolution rule for sets of clauses. And here I denote F resolved with G, where F and G are sets of clauses, as the set of all resolvents with clauses from F and clauses of B upon X. And what you require is that the resolvent is not a tautology. So all non-tautological resolvents upon variable X. You could view this a bit like a join in relational algebra if you want. Not really, but the idea is similar. Now, if you're given a literal x, you define the formula fx as basically the set of all classes of f that contain x. And once you have this, you can define variable elimination as follows. So given a CNF formula f, variable elimination, also called DP resolution, removes the variable x by replacing the sets fx and f naught x with the set fx resolution joined with f naught x. And actually, if you do this until fixed point, so you pick a variable, you eliminate it, you pick the next variable, you eliminate it, and you go on until a fixed point, then what you get is either the empty formula, which clearly is satisfiable, or the empty clause, which clearly is unsatisfiable. And so you have a full proof procedure for propositional logic as introduced originally by Davis and Putnam, very popular. Basically, the first nice proof system or proof procedure that current SAT solving is now based on, but it's just all with way more details nowadays. And here's an example. For instance, if on the top you have these three clauses that contain x, that's your fx, and on the left you have the clauses that contain not x. And then you consider all resolvents, like here you have not x or a resolved with x or c, then you get a or c. And here, if you do not x, I think you get it. And then the only thing that remains is that if you look at the two clauses on the top right here, you can remove them because this here contains a or not a, and this here contains b or not b, so they're tautologies. But still now, when you look at the result of this resolution, then you will notice something, namely that here we started out with 6 clauses and we ended up with 7 clauses. And that's not too bad, but in general, what you can get when you do this is you can get exponential growth. And that will really blow up everything, your clause set, which is bad. The question is, what can you do? And what you can do is when you do variable elimination, you do it just on variables where there is no blow up, where the resulting set of formula of clauses is no larger than what you had before. Now that's what you would do, and this avoids the exponential growth that you have when you do naive variable elimination. Now, like in Austria, for instance, in politics, it's very common that we like to come up with many rules, we specify them in lots of detail, and it's all fleshed out nicely, but then when push comes to shove, in the end, you don't stick to the rules, you just do something a little different, and it's all fine, and everybody agrees that that's okay. And that's also what happens here in practice, because you don't really stick to the rule nowadays. You say you loosen it a bit, and what you do is you say, okay, we can increase this bound incrementally as long as the size increase that we get from eliminating variables is moderate, or whatever that means. And as I said, this is arguably the most important preprocessing techniques. When it was first introduced into the SAT competition, it led, together with other things, to the largest improvement of solver performance that had been witnessed until then, and I think until today. And what's nice is that it's particularly effective if you combine it with subsumption. So you eliminate the variable, you add the resolvents, and then you perform subsumption. You remove subsumed clauses, for instance, or you combine it with blocked clause elimination, which is another type of clause elimination technique for preprocessing. And that one I will get to next. So,
Benjamin, there's one question in the chat regarding, so if you eliminate a variable with bounded variable elimination, how do you get the solution where the variable that is eliminated is for the solution for the original formula?
So that is a very good question. Normally what you do is when you go up your resolution tree, you can reconstruct the assignment from looking at your assignment tree and seeing, you always know it must make one of the clauses true if so your resolved clauses are true. this means that one of the two clauses from which it was resolved must be true by the same assignment. And then you can just pick one of the literals, one phase of the literal, and make it true, because one of the clauses must be true anyhow, and the other one will be true if you make your literal true. Does that make sense? Or is that...
Ziad, is it clear? No, he's an entity, so he cannot answer.
Yeah, maybe we can get back to that afterwards.
Yeah, sounds good.
Yeah. So, Marijn, do you have the time? How long is, how far in are we?
We are it's now 11 noon, but here, so you have, but you have a little bit more time. Just
maybe let's see if I'll then skip hyperbinary resolution. We'll see. But let's move on. So block clauses. So we saw that you can remove clauses that are redundant, meaning that they don't really affect what your solver does. But for these clauses, actually what we saw, like for tautologies, what you get is if an assignment makes your formula true, then that assignment also makes your formula true after you removed the clause. And the same is true for subsumed clauses. Now with blocked clauses, you loosen this requirement a bit and say, I don't exactly need the formulas before removing the clause and after removing the clause to be satisfied by the same assignments. I'm fine if I just know that if the result is satisfiable, or if the original formula is satisfiable, then the result is also satisfiable, or if they're both unsatisfiable. So you really just care about the satisfiability status, but not about the actual assignments that you're considering. And you say a clause is blocked if all resolvents of that clause upon one of its literals are tautologies. And here's an example. So we have the clause C, and now we pick one of its literals, in this case B, and we consider all resolvents upon this literal. And in this case, we can resolve with the two clauses in the middle because they contain not B. We can ignore the other two clauses because they don't contain not B. And then we look at the actual resolvents. And what we get is that one resolvent would be X or Y or not Y, and the other one would be X or Y or not X. And in both, we have complementary literals. And that means that the clause is blocked. They're tautologies, so the clause is blocked. All resolvents are tautologies. More formally, as defined by Kuhlmann originally when he introduced the concept of a blocked clause, they say a clause is blocked by a literal B in formula F if for every clause D that contains not B, the resolvent of C and D upon B is a tautology. Now, you can prove that if C is blocked in F, then F and not C are equisatisfiable. And that proof is actually not too hard, but I'll not give it here, but it's pretty much straightforward. And now in preprocessing, when you do block clause elimination, you just start with a formula F and you remove block clauses until no clause is blocked in F, which is not 100% true, because sometimes you might not want to run block clause elimination until a fixed point, but just until some time limit or something. But you can run it until fixed point, and that's how I define it here. And here's an example. This formula A or B and so on. Here, if you take a closer look, you could see that the middle clause is blocked, so you could remove it, and the same holds true for the last clause. And once you remove one of them, the first clause also becomes blocked, and then you can also remove it. And what happens here is that in this case, block clause elimination could remove all of your clauses. So you can see that by removing certain clauses, new clauses can become blocked and so on, and then you can go on removing clauses, and this can lead to the removal of many clauses. And what you can actually show is that block clause elimination, if you do it until fixed point, is confluent, meaning that the order of eliminations does not affect the outcome. So you just check non-deterministically, you pick a blocked clause, you remove it. Then you pick the next blocked clause. New clauses might become blocked, you remove them too. But however you do it, in no matter what order, you will always get the same result. And actually the same is true also for block clause elimination in first order logic. So not only in propositional logic. The cool thing about block clause elimination is that it can do many nice things. Like when you convert a formula that is not in conjunctive normal form into conjunctive normal form, then you could use the Zetin encoding, which is usually used in practice. But there's also the Placed-Greenbaum encoding, which is basically a subset of Zetin. And what you can show is that actually, if you apply block clause elimination to the Zetin encoding, you can get the Placed-Greenbaum encoding. And likewise, you can do a few circuit simplification techniques that are simulated if you do them on a CNF, like if you know them pure literal elimination or cone of influence. And here's an example where you do circuit simplification. I'm not going into the details here, but this would be the encoding of the circuit. And you can, if you take the time to check it, you can see that by block clause elimination, you can actually start removing these clauses and then those and so on. And you basically remove everything here. Now, one more thing, I said that it's not always the same assignments that satisfy the formula before and after preprocessing. So there's a technique for solution reconstruction, and this is very straightforward. Actually, linear, as you can see, at least this while over the stack of eliminated block clauses. So while you do block clause elimination, you save your block clauses together with the literal that blocked them. And then you take your formula and start with an assignment that satisfies your formula. That would be your resulting formula of the preprocessing. And then you just go, you pop literals from your stack. You start with the first one. Then you check your assignment. If it falsifies your clause, if it doesn't falsify your clause, then you're fine. Your assignment satisfies the formula even if you add C. And if not, you just make the blocking literal true. And that's it. And it's guaranteed that this satisfies the outcome. And you do this continuously until you're done with all your clauses. And then you return the assignment and you're fine. And why this works is basically based on this proof that I mentioned, why block clauses are redundant and can be removed. So do we have more time for hyperbinary resolution, or should I jump straight to the concluding remarks?
I think you better go to the concluding remarks.
Yeah. All right. So as a conclusion, I mentioned that there are many techniques, and that here I just considered a few of them. But there are really many, like we saw subsumption, variable elimination, block clause elimination. Unfortunately, we didn't see hyperbinary resolution, but there are also others like bounded variable addition, equivalent literal substitution, what have you. And the list is growing. There will come more and more preprocessing techniques. And as I mentioned in the beginning, unfortunately, it's not always clear what does or does not work in practice. And that really depends a lot on the formula at hand. So what that means is that if you have a certain formula and your SAT solver can't solve it, you might want to play around with using preprocessing techniques. And I think Maranin is a great example for this when he solved the Pythagorean triples problem, because he had this nice mathematical problem that no one could solve. And he, of course, with his experience, saw that many of the clauses that he got when he encoded the problem into propositional logic were blocked clauses. So he could eliminate many of them with block clause elimination, and it worked. So you might really want to consider using some of the techniques, because maybe if they don't work well in general, they might work on the formulas you're dealing with in your application domain, be it software verification or whatever. Now, I've only given you a very high-level talk, as I mentioned in the beginning, but if you want to get more details, then I recommend you have a look at the Handbook of Satisfiability, because the second edition was published just recently, and it now contains, in contrast to the first edition, also an article on preprocessing that contains many, many details on the things I mentioned during the talk, and also many more techniques and background and references. So with that, thank you. And if you have any questions, glad to answer them.
Many thanks for this very nice talk, Benjamin. Yes, I want to just repeat it. Who has questions? So maybe you can kind of start with maybe answering a bit more what Ziad mentioned regarding variable elimination, because how kind of can you use this algorithm for block clauses also for variable elimination?
How you can use the block clause algorithm for you mean the solution reconstruction? Yeah. So you eliminate variables one by one, right?
Yeah.
And then when you add them again, you know that all the clauses that you resolved from must have a satisfying assignment if the resulting resolvents can be satisfied. But those clauses, they contain either the literal in one phase or in another phase. And then you just look at, when you add the variables again, what phase do you need to make true to make the original clauses true? And then you pick the literal in one of these phases and you add it, and you do this continuously for your whole formula, and then you will end up with a satisfying assignment of your original formula. And I think, couldn't you even show that it doesn't even matter in many cases, and you just add whatever phase you want? Would need to look into the details again.
I don't think so. I think as soon as clauses form a definition, right, there's only one way you can
yeah, that's true.
Maybe you can tell a little bit more about kind of your own preprocessing work, and also, for example, do you see, for example, that you can have a useful kind of PR addition preprocessing in the future? Do you see something like this happening, for example, as done?
Yeah. So what I was working on mainly was, on the one hand, to come up with generalizations of block clauses. So we saw that that was one thing. When you look at the block clause, for instance, you say it's a clause where all resolvents on one literal are tautologies. So together with Amin and Martina, and then later also with you, we looked if you can do something more general, not only requiring that there's a literal when you resolve it away, you get tautologies, but for instance, a set of literals in your clause, that when you do some kind of resolution generalized to sets, you still get tautologies. And you could take this idea further and so on, but what you get is clauses, types of clauses that include blocked clauses, but that are even more clauses of which you know that they're redundant. Now, first we thought it might be a good idea to remove them, but it later turned out that adding them makes more sense. And what you can show is that by adding these more general clauses, those generalizations of block clauses, you can define proof systems where you say, okay, here's my proof system. I get a formula in CNF, and I can add new clauses if they're, for instance, blocked clauses or more general types of redundant clauses. And what you then get with these more general types of clauses is that you can often get very short proofs of popular formulas for which you don't have short proofs with resolution, for instance, and for which you might have short proofs in systems like extended resolution. But in those systems, you introduce new variables with definitions, as you mentioned before. But with those stronger proof systems, you can actually avoid adding new variables and still get very nice short proofs based on adding what's basically redundant clause.
Yeah, cool. So there's also one question on YouTube, and that's what SAT solving is happening at SAP?
What SAT solving is happening at SAP? Well, SAT solving itself, not much, but there's currently a team in Newport Beach. I'm not sure how much I'm allowed to tell you here, but you know that SAP has this programming language called ABAP, which is very SAP related. And what happens a lot in practice is people have old code in ABAP and they don't want to touch it because this is legacy code. Nobody wants to touch it because if you change a thing here or there, might ruin everything, right? So you have this legacy code that nobody dares to touch. But colleagues in Newport Beach are now looking into using SMT solvers to prove program equivalence of ABAP programs in certain situations, so that if someone touches the code, if they can guarantee with the SMT solver that what they produced is equivalent to the original program, then the simplification of the code was safe. Now everybody knows that in general, program equivalence is undecidable. I don't have to tell you this, but in certain special cases and with restricted syntax, this can actually work. That's one thing that's currently done at SAP.
Okay, cool to hear that more and more companies are using this technology, right? Emre has a question. Would you like to do this directly, Emre?
Sure. So I'm referring to, like, I guess, some slide in the first 10 slides. You mentioned, like, when talking about pre-processing, yeah, around here. So removing the wrong things can have disastrous consequences. Is it like an observed disastrous consequence, or is it like a proved disastrous consequence?
So that's a good question. What I'm here, like what I imagine when I say that removing the wrong things can have disastrous consequences, in particular is something that's kind of a proof, but it's not really a proof because it's a simple observation. So if you're familiar with proof theory, with proof complexity in propositional logic, for instance, you know that the pigeonhole formulas, this is a well-known kind of formulas in propositional logic. They only have resolution proofs of exponential size depending on some parameter n. Now, most normal SAT solvers are based on resolution, and that means that these formulas, your SAT solver will take exponential time on the formulas. Now, what you can do, however, is you can add certain definition clauses to the pigeonhole formulas, and suddenly everything will be way easier for your SAT solver, and you get an exponential speed up. And now, imagine it the other way around. Now think about the following. You have added these nice definition clauses. Now your solver should in theory be fast, but now your pre-processing technique comes, and actually blocked clause elimination that I mentioned removes definitions. So it would remove your nice definitions, and what you end up with is then the formula that takes exponentially longer. So that's one example.
Yeah. Are there any other questions? In that case, Benjamin, I would like to thank you again for this very nice talk.
Thank you.
And could you then stop sharing? And Jeremias, could you start sharing?